All right, everyone, let's get started. Welcome to lecture number 12 of Deep Generative Models. So today we'll talk about a particular class of unnormalized generative models, which are also called energy-based models. And even though energy-based models are, in some sense, the oldest class of generative models, historically speaking, it turns out that there is some recent development that made them, again, important and fashionable, while there was sort of like a couple of years where they were a little bit underappreciated, and now they're sort of coming back. And as usual, before I forget it, actually, about the homeworks. So as you might have realized, we released homework number 3, and so we extended the homework deadline so that you have one more week. So it's going to be due now on November 19th. So the week before the Halloween week, the Thanksgiving week. But still the project abstract deadline is still going to be the old date. So that's going to be November 12th, right? So remember, there you have to decide on essentially what you want to work with your team, right? And write this abstract. Okay. All right, so far we've talked about generative models, and in particular, we talked about how to represent them. For example, we learned to distinguish between so-called latent variable models that have like some unobserved part in them, and then fully observed models, such as normalizing flows or autoregressive models. We talked about different objective functions and different optimization algorithms. For example, we talked about different divergence metrics that you could use as a criterion to fit the generative models distribution to the data distribution. So for example, Jensen-Shannon divergence or KL divergence. And some of them were likelihood-based and others were likelihood-free. For example, GANs were likelihood-free approaches. And yeah, as I already mentioned, today we'll talk about a very different class of models with its own problems, and those are energy-based models. Okay. Yeah, first of all, should be clear by now that like probability distributions are core to generative modeling, right? They are kind of a essential building block that we use in one or the other form in all of these different versions. And of course, they have like two properties that we ask that probabilities should satisfy. I mean, first of all, probabilities should always be non-negative, right? That's pretty clear. And then also they should sum up to 1. Right? If there are discrete states for x, and if x is a continuous variable, and then we have the notion of a probability density, and we ask that this probability density integrates to 1. And today we'll talk about something that we never really talked about much so far, namely the second aspect, that probabilities better integrate up to 1. So in other words, if you take away a piece of a cake, then obviously what remains from the cake is going to be reduced because the total cake volume is supposed to be normalized, right? So and that turns out to be crucial, right? This normalization constraint when we talk about energy-based models. And it turns out that the whole difficulty associated with training energy-based models comes actually from that normalization constraint. Yeah, so this basically means that the total volume under that probability distribution P of x should be fixed, such that when we actually increase the likelihood of our training data, automatically we're actually reducing the likelihoods of some other data. right? Because the total probability mass under that distribution is constrained. Right? And so in other words, one way to think about it is that we actually make the training data relatively more likely compared to other data points, right, that we didn't train on. Yeah, so those are, again, these two requirements of probability distributions. And now, you know, how do we actually, how could we then design these probability distributions? How can we kind of invent distributions that we use to model the data? And in particular, the first requirement is typically fairly easy, right? Any non-negative function will do the job, right? So basically just coming with some non-negative function that we parameterize with certain parameters theta, for example, using a neural network in some way, is typically not very hard. For example, we learned about different tricks to ensure positivity of a neural network, right? So for example, you could just square the output of some function f, right, and call that g. Then by construction, g can never have negative values, right? So potentially you could use g to parameterize a probability density over x. However, the big, and another sort of more popular and more common approach that we'll mainly talk about in today's lecture is you can actually also exponentiate f, right? And if f is an arbitrary function, then the exponential of f is, again, a positive function. Yeah, of course, there are many possibilities. Now, this is actually easy, just kind of designing some function over our data space X that is just simply positive, can be easily achieved. But the problem is actually to make sure that this function actually also integrates to 1, right? Or if X is discrete, that the G evaluated at these Xi's sum up to 1, right? This constraint turns out to be much more difficult to enforce. Yeah, so as follows, we'll oftentimes talk about this object here, z of theta, which is the sum over, some function that takes values that assumes data points as inputs, and we sum over all of the possible data points we can take as inputs. Right? So the sum over all x of g of theta will be called z. It's also called partition function, and we'll talk later more about it. And so that is usually by default not necessarily 1, right? Unless we make special choices for g or f. And so g theta in general is not a valid probability mass function or a probability density function. Okay. All right. So to sum up, we just learned that this coming up with some function g theta of x that is non-negative is easy, but making sure that it's actually normalized in general is going to be hard. Now, what is an easy fix to that? Well, the simple fix is just to slightly redefine the resulting probability density that we want to construct based on that function g. Namely, instead of just saying g equals the probability density, we just explicitly normalize that function. In other words, we're dividing it by the volume under that function g of theta. Right? And by that I mean I explicitly normalize g of theta by dividing it or multiplying it with a scalar, and that scalar is exactly 1 divided by the integral of g theta over all possible values of x. Right? So now by construction, this gives us a normalized probability density over x. Yeah, so by definition, then P now integrates to 1. Yeah, and so traditionally in statistics, for example, or in classical machine learning, we would choose g theta of x so that we actually know this integral analytically. In particular, how this integral or this volume behaves as we change the parameter theta of that distribution. So just to kind of give you a couple of examples. So let's imagine we're now in 1 dimension. Then if I define g of x to be the exponential of a quadratic, namely x minus some mu squared divided by 2 sigma squared, then we can explicitly compute this normalization constant. using the fact that this exponential is actually integrates to the square root of 2 pi sigma squared. Right? And of course, you all know this already from the Gaussian distribution. Right? So that's explicitly where that normalization constant comes from. Another example is the exponential distribution defined over the positive reals. So here we actually define g lambda of theta to be the exponential of some negative lambda times x. And in order to make sure that we can convert this into a distribution that's actually normalized, we compute its integral, this time ranging from 0 to plus infinity. And this actually turns out to give us 1 divided by lambda. Right? So now we can multiply this thing by lambda, and it results in an exponential distribution that is normalized. Okay. Yeah, so what's the requirement of this approach? Well, we need to restrict our attention to functional forms for G that we can actually easily integrate analytically. But this is actually like a huge constraint, because in practice, as you can imagine, that can typically only work either if we're drastically restricting the power of G, or we're focusing our attention to low dimensions, for example, one-dimensional cases, right? In these cases, oftentimes we come up with examples where we can compute these integrals easily. But if we want to use G to parameterize some really high-dimensional distribution over images, like millions of dimensions over pixels, then you could imagine that by default, it will be very hard to come up with a good functional form of G that is actually, that you can explicitly integrate. Okay, there's a question over there. This one? Yeah. Should the volume be? Oh, yeah. Good point. Yeah, thanks. I'll correct that. Yeah. Mm-hmm. Okay. Any questions so far? All right. So the question then is like, how can we potentially deal with these models, even if we're maybe unable to explicitly integrate them and compute the normalization constant? Are there maybe some tricks to get around computing these normalization constants in general? Yeah. All right. So this is just like copying the formula from before. Implicitly, we have actually already made use of this normalization requirement in the past, right? When we constructed deep generative models, we sort of found our ways of getting around these problems, right? So maybe we haven't paid a lot of attention to what we actually did there. So let me be very explicit about that. So for example, so how did we oftentimes make sure that these distributions that we use to parameterize data actually integrate up to 1? Now, one example are autoregressive models that we discussed pretty early on, right? An autoregressive model, as you remember, uses the chain rule of probability to write a joint distribution over x and y into a product over x, distribution over x, and then a conditional distribution of y given x. Okay? And typically, the way we understand this is that the dependence of x on x of that distribution over y is actually sort of hidden in the parameters of that model, right? So oftentimes we use neural network parameters and, for example, a recurrent neural network or something. And then the hidden state of that recurrent neural network would know about the previous generated data point. And so dependence on x is sort of via the parameters theta2. So how does an autoregressive model here in this very simple case with only 2 variables exploit the fact that it's already normalized, or why is it actually normalized? Well, you can actually easily check that, right? You just write down that joint distribution over x and y. You're just copying that expression from before, and now we integrate over x and y. Now, first of all, I can sort of pull out this p of theta 1 of x out of the integral over y, because that doesn't depend on y. Right, so this is an outer integral over x. Then we have a p of x, and an inner integral over y. And now we just have that second expression in here. Now, the point here is that for any x, right, x only influences the parameters, theta2. For any x, this thing here is actually already a normalized distribution, right? So this is just 1, right? And so then we're only left with that second factor, p over x, and this is also a normalized distribution. So it was actually already sort of automatically built in that we work with building blocks that are valid probability distributions. Another example are latent variable models. So how did we sort of deal with the fact that these distributions have to be normalized in this case? So for example, think of a mixture of two distributions, like you can think of P1 and P theta 1 and P theta 2 as two different Gaussian components. And like if we work with mixtures, then we weight them with some weights that sum up to 1. So we have an alpha of P of theta 1 plus a 1 minus alpha of P of theta 2 as an example. And if we want to compute this normalization, well, you know, the integral of the sum of these two distributions is just like the sum of these two integrals. So in both cases, I can sort of pull out these constant factors, alpha and 1 minus alpha. The individual components are integrating to 1. And so I'm just getting alpha plus 1 minus alpha, which equals to 1. Right? And so that was essentially the idea of how we dealt with in terms of latent variable models with that normalization problem. Yeah, but how about using models where this normalization constant is actually not as easy to compute, or maybe even impossible to compute, right? Maybe that actually would open up like a totally richer family of models that are very expressive and very useful in practice. So we want to talk about strategies of designing or parameterizing densities over data while we're not explicitly able to compute the corresponding normalization constants. Right? And those are called energy-based models. So what's now the definition of an energy-based model? Well, it's just like some arbitrary distribution over some high-dimensional data x that satisfies a particular parametric form. So it's just defined as an exponential of some function f over x, and then we explicitly normalize that expression by dividing it by the volume of that exponential of f. And in particular, we oftentimes want to give this normalization factor here a name, and we call it the partition function z. It's actually it's called z because it comes from physics, and it has a funny name because, as you might know, a lot of physics in the early 20th century happened in Germany back then, and so it was actually called Zustandssumme. I think that's where z comes from. Really impossible to pronounce, I guess, for non-German, Zustandssumme. Anyway, that's where that letter z comes from, and in English it's called partition function. So it's the definition of, you can also call it the normalizing constant that makes sure that this expression actually integrates to 1. Okay. Yeah, so z is defined as the integral of the exponential, and it's called partition function. Now you might ask, why is it actually exponential and not just like something squared? Because the reason we exponentiate f was, as you remember, to ensure that it's positive or non-negative in the first place. Well, there are a couple of reasons. Oftentimes we want to sort of capture a lot of variation in probability, right? So probabilities can range, I mean, they're between 0 and 1, but they are oftentimes, well, densities can actually be even larger than 1, right? They only have to integrate to kind of to finite values over finite volumes. But the point here is that, you know, there's a huge range typically in probabilities, right? Oftentimes probabilities are extremely small, 10 to the minus 4, 10 to the minus 10. And we want to be more easily able to capture these large variations in probabilities. And therefore, it's easier to work on a logarithmic scale, right? So if we already know that the exponential of f varies on an exponential scale, then, you know, then we should actually operate on a logarithmic scale, and therefore it's natural to parameterize these probabilities as exponential of something, right? There's also another reason, namely a lot of classical probability distributions, like for example the Gaussian distribution, the exponential distribution, and many others, belong to the so-called exponential family in statistics. And there are many known results about exponential family distributions. And so this is like a way of adopting that notation and that language of exponential families. And finally, as I already said earlier, energy-based models actually arise under fairly general assumptions in statistical physics, in particular in equilibrium thermodynamics. And you can actually derive that functional form in many cases under the principle of maximum entropy, or the second law of thermodynamics, right? And so that's actually where these come from, where they naturally arise. And then only later on, they will actually adopt it in the computer science community in the 80s and were shown to be useful in machine learning much later. Yeah, in physics, negative f of x would be called the energy. And therefore, those are called energy-based models. And the distribution that results from that is then called a Boltzmann distribution. So maybe you've heard about Boltzmann distributions at some point. Okay. Any questions so far? I mean, so far we've only made definitions pretty much. All right. Okay. So here's once more that energy-based model. So what are some pros and cons of the energy-based model? Well, first of all, it's very general, right? It's much more general than latent variable models or autoregressive models. You can pretty much plug in any function over your high-dimensional data that you want. That means you can come up with any crazy neural network architecture, convolutional or not, or transformer or whatever you like over your entire data input, and you can convert it into an energy-based model, right? So that's very powerful, of course. But what are the cons, the disadvantages? And it turns out there's actually a huge list of them, right? So it turns out that many things are much more complicated in energy-based models, which is sort of why they got out of favor in the last 10 years, after they actually originally led to some progress in deep learning, then they kind of got out of favor, and now they're sort of coming back. So why are they difficult? It's actually very hard to sample from these distributions. Right? We know how to sample from a Gaussian distribution, but we don't know how to sample from a really high-dimensional complicated distribution. Right? We need actually sampling algorithms, and we'll talk later about that to even be able to sample from them. It's also pretty hard to evaluate and thereby optimize, and therefore optimize the likelihood of P of x exactly. So it turns out it's actually impossible, and so we have to kind of come up with approximations. Right? So why is it hard to evaluate the likelihood? Anybody give an answer? Intractable integral, yeah, exactly. Right? So you can plug any data point in here in a trained model. So you will be able to evaluate this exponential, but you don't know the normalization constant. Right? So you basically know the likelihoods up to a multiplicative factor, but that factor just turns out to be important. Yeah, what's another disadvantage? You can actually not learn any features, which has to do with the fact that, there's not a low-dimensional representation emerging from these models, typically. But that was also the case, for example, for autoregressive models. Yeah. So those are kind of a lot of disadvantages, but we'll still learn about solving some of these problems that we described here. Now, one idea might be, well, can't we just compute the normalization constant numerically, right? Aren't we pretty good at numerical integration? And the answer is, well, yeah, maybe if it's like 5-dimensional or 10-dimensional, right? You might still be able to use kind of numerics to do that integration. But here we're talking about million dimensions, right? And so analytical integration even numerical integration is simply out of question in these really high-dimensional spaces. Yeah. However, the good news is that actually some tasks don't actually require knowing that normalization constant z. And this is exactly what we'll exploit when it comes to training these models. Okay. Any questions? All right. Okay. So what actually are the things that we can easily do? Well, first of all, if we take, again, an energy-based model, and we take two different data points, x and x prime, and our goal is to evaluate the probabilities of x and x prime, this is actually still hard, right? Because as we talked about, this actually requires us to know the normalization constant. However, if we only want to decide which of the two data points is more likely than the other, all we care about is actually the probability ratio, not the absolute probabilities. Right? So in other words, p theta of x divided by p of x prime. And if you compute this ratio, you will actually see that the normalization constants drop out, right? They're identical between both data points, and therefore they cancel out. And all you're left with is sort of the unnormalized part of that distribution. And this actually turns out to be easily to be evaluated, right? You just put x and x prime into f, you take the difference and exponentiate it and get an answer. Okay. And so this is good. So we can basically easily check among two data points which one is the more likely one. And this actually can oftentimes be useful, for example, in anomaly detection applications or in denoising applications. And we'll actually later also talk about where we used some related tricks also for training these models. Okay, so where are they actually being used? So as I mentioned earlier, they have this interesting history that they actually emerged in the late 2000s, before 2010, and showed great successes there as almost one of the first class of deep models that were giving really good results. And basically, here's a really old, an older paper, from Jan LeCun in 2006, where these models were exactly shown to perform good at kind of compare, a task in which you kind of compare different data points together, right? I mean, for example, you can associate images with text, you can associate handwritten text with written text, and many different things. And that was sort of like early applications of these models in the early 2000s. Another really important and popular model is the so-called Ising model. Ising models are also originally models that originated from physics, where they were actually used to simulate magnetism. I'll quickly comment on that later on. And then in the 80s, they were actually proven to be useful in certain computer vision tasks, such as, for example, image denoising. So nowadays, there are better ways of doing image denoising, but there's some kind of really nice ideas around here, these old Ising models, and they're very well known. So what is then an Ising model? So typically there are so-called lattice models, as you see here, where you have multiple random variables that are sort of sitting on a lattice. For example, you can think of them as pixels in an image, right? So here we would have like a 3x3 pixel image. Let's imagine it's a black and white image, right? So kind of really small image. Then Y would be, and oftentimes in these image models, the Ising model was typically used as a model for denoising an image. And so the idea here is that you only observe an image X that is actually corrupted by noise, and you're interested in sort of restoring the original noise-free image. Now, the configuration of black and white pixels of the noisy image would be then denoted by X, and the sort of idealized underlying image would be Y, right? Now those are also called Markov random fields, and here's like an underlying model of how to think about them. So let's first look at the formulas and then kind of go back to that image. So it turns out that they actually formulate a joint distribution over the true image X and sort of the assumed underlying uncorrupted image Y. And this model takes, again, an energy-based model's form. So it's 1 divided by its normalization times the exponential of some energy, right? And this energy here has the following form. It's a sum over all pixel locations I. And here we have sort of these little energies, phi I, that depend on xi and yi. So those are kind of some coupling terms that express a joint energy over every pixel's location, and it's kind of corrupted version and its true version, right? So for example, these x's here are the green dots here, and the underlying y's are the orange ones. And so the first term only looks at these correspondences in the vertical direction, right? So these are associated with the edges that you see here that are kind of going out of the canvas of that image. And then there's another energy term here, which sums over pairs of pixel locations, I and j. And this term is actually looking at the configurations of yi and yj, so these kind of assumed ground truth pixel values at nearest neighbors on that image geometry. Yeah, so what do these two different terms do? So let me first build up that slide. So first of all, the first term that looks at xi and yi tries to sort of enforce alignment, right? It's basically saying that, if the observed pixel is black, then with very high likelihood, the underlying pixel is also black. And if the observed pixel is white, then it's more likely to be white. But the important part is it's not 100% certain about it, right? It's just like some inductive bias. And then the other term here, the coupling term among the y's, is basically expressing that nearby pixels should have similar values, right? If a pixel at a certain location is black, then with higher likelihood the surrounding pixels are also black than they are white, right? If that was not true, then the image would have no structure. It would look like random noise. But generally, for structured images, it's more likely that the surrounding pixel has the same color compared to the reference pixel. Yeah, and so this can be achieved by just choosing j to be a constant and then just multiplying yi times yj, assuming that the binary value is actually -1 and +1, right? So then if they're the same, then this is always +1 and you have like a positive energy cost. If they're opposite, then it's kind of a negative value and that will be penalized in that model. Okay. Yeah, so basically now when you then ask for maximum likelihood, you have to do inference over y. So you have to find the configuration of y's that minimize the energy, right? And there are sort of algorithms that do that for you. Yeah, so essentially you're interested in maximizing a conditional probability over y's given an observed input image x. Any questions so far? I mean, this is not even a deep generative model, right? As you observe, there's no neural networks anywhere. It's explicitly expressed, but it's clearly a generative model because once the model is trained, you can potentially generate random images with it, and they might look locally coherent. Well, it will be pretty hard to generate any high resolution images from that model. Okay. All right. Yeah, so another important area in which unnormalized probabilistic models appear, or energy-based models appear, are so-called situations in which you build products of experts. So what's a product of experts? It's basically building combined models out of individual models, where you don't trust every individual models, but you're sort of trying to aggregate them, right, to kind of arrive at a better model. So imagine you have already trained models, three different models, P, Q, and R, and they have different parameters, θ1, θ2, and θ3, right? All of them are already trained models. For example, one could be a pixel CNN, another one could be a normalizing flow, and the third one could be a variational autoencoder or something like that. Now, and each one is actually an expert that you're actually that you're actually trusting in particular regions. And you want to sort of aggregate these three different models into a combined model. Now, what you want to do is you want to score how likely every individual data point X is. Now, if you assume that these experts are making their judgments independently, then a natural way to combine them is actually through a product, right? So then you're interested in the product distribution of P, Q, and R. And of course, this product is now no longer normalized to one, right? The domain is sort of the same of these three different distributions. So the product of any two distributions in the same domain is no longer a normalized distribution, and of course also not for three. So what you have to do then is you have to explicitly normalize it. And now this allows you to kind of write down that product of experts distribution that now depends on these three different parameters. And it's, again, assumes the form of an energy-based model. Right? It has an explicit normalization constant that you need to compute. It's a little bit like a mixture model, right? You could also have imagined that instead of multiplying these three different distributions and normalizing them manually, you could also just have associated weights with all of these three different distributions. But this will actually serve very different purposes, right? In the case of a mixture model, you're basically happy if one out of these three different distributions assigns high likelihoods to any data point. And so then the resulting mixture will also have a relatively high likelihood. In the product of experts, the situation is different. You only get high likelihoods if all three of the distributions have support or have high probabilities, right? The one that's kind of scoring the lowest probability will sort of dominate, and the overall probability will be low. Right? So in some sense, it's like a logical AND operation. So all three experts have to be happy. Whereas like the mixture model is like, it's more like a logical OR in which one of the three experts has to be happy with the data, right? But yeah, so both of them can be very powerful models.
I have a question really quickly. Could you go back to the last slide?
Okay. So there's one model that you might have heard about. It's also mainly of historical importance, the so-called restricted Boltzmann machine, or RBM. This is also an energy-based model that was very popular again in the early 2000s. And it was actually an energy-based model with latent variables. And the combination actually allowed it to be very efficiently to be computed, and you could actually generate data from it. So what's the restricted Boltzmann machine? So it turns out you have two sets of random variables, X and Z. They have, by default, they have different dimensions. X is sort of the visible part. For example, if you want to model images, then those would be the pixel locations. And Z are have some other dimensions, and those are the latent variables, like similar to a variational autoencoder, right? But in a totally different architecture. Now, this restricted Boltzmann machine is expressed as follows. It's again an energy-based model, 1 over Z times exponential of some energy. And the energy is as follows. It's like the matrix product of the data vector X transposed. Then you have a matrix of learnable parameters W and another vector of these latent variables Z, right? Plus a bias term for X and plus a bias term for Z. Yeah, so here it's kind of once more written out explicitly. Now, the important part to see here, so first of all, this is the diagram, right? You see that basically the visible units, X, they are all connected to all possible hidden units. And so also the hidden units are connected to the visible units. But importantly, there are no cross connections. There are no connections among the hidden units, and there are no connections among the visible units, right? And so in other words, there's sort of, for example, there's missing a term like X transposed W prime X, right? So that would be a coupling term among X, and that is just not part of the model. So it turns out that this will later on, and we'll talk more about it, is actually important for doing efficient inference in these models, right? So that was an important trick. And it turns out that if you then marginalize out these latent variables, then you actually induce a complicated distribution over X, which you, for example, can use in order to, generate something. Yeah, it's restricted because exactly of these constraints. There are no visible connections, and there are also no hidden connections. In other words, these coupling terms xi times xj or zi times zj simply don't exist, and this is actually why the model is going to be tractable later on. So it turns out that these deep Boltzmann machines could also be made deep. That was like one of the first successes of deep learning, where you essentially actually an unsupervised architecture, really, right? So you have here the base level, which is your input data, and then you have a first stack of latent variables, and you see that there are only cross connections between the data and these latent variables, but not among those latent variables. But then you can actually add connections to higher level latent variables, and you can really make that architecture deep. Right? So the way this was actually trained back then was not jointly because of vanishing gradient problems, or actually because this kind of learning algorithm had to operate in this particular fashion. But if you were doing greedy layer-wise training, then you could actually stack more and more latent variables on top of that architecture, and therefore make it more and more powerful. Yeah, so this already had like the property that we're used to nowadays in deep learning, that sort of lower level layers sort of encode low level features, and higher level layers encode high level features, as you might have already seen in many examples. Okay. All right. Yeah, so here are some early results. From the really dark ages of the third wave of AI. So we have here the training examples. You see some simple black and white images of some toys. And then when you trained this restricted Boltzmann machine, the deep restricted Boltzmann machine on that, you could actually generate these kind of images, right? And they're not kind of, it's not just memorizing, it's really sort of generating new images, right? So that was kind of quite impressive back then, right? Because you might have to imagine, before, yeah, in the 90s, there was just no single model available that could like generate anything structured like that, right? So all of that is relatively recent. Okay. All right. So we talked a lot about, reasons why these models are difficult. We talked about particular examples and particular instances of models and how you could encounter them, even if you work with building blocks that were not generative, that were not necessarily energy-based models. But how do we actually train them, and how do we use them in practice? Right? So that's going to be happening next. All right, so here once more is the formula. And yeah, this is actually just repeating the pros and cons that we've already talked about. Again, the pros is it's very powerful. The con is that you can't even sample from them. It's hard to evaluate the likelihood because you do not know the normalization constant, and you also cannot learn features. So how then can you actually deal with these models? And here's one example. Let's actually consider the restricted Boltzmann machine example once more. Again, here's the expression as a energy-based model involving that particular energy where no x and z are paired, where no x and x coordinates are paired and no z and z coordinates are paired. And again, x are the visible variables and z are these latent variables. Yeah. So it turns out then that in this case, both x and z are discrete. And what would we actually have to compute if we were to compute the normalization constant of that? Well, we have to sum over all possible values that x can take, right? In 0, 1 to the power n. So n is the number of pixels in an image. And similarly, z out of all possible combinations of zi, being 0 or 1 individually. And then kind of look at the exponential of that energy. Now, the problem is that this is actually exponential, right? It's basically exponential in the dimensions. And so in other words, the computing time is really exponential in both n and also in m, right? And both are sort of typically in the thousands, if not even in the millions, if you wanted to scale it up to modern full resolution images. So that is usually completely intractable, right? And just because you cannot even compute the normalization constant, it means that you cannot compute the likelihood. And if you cannot compute the likelihood, then you cannot learn the model. You cannot train the model, right? Because typically you want to aim for maximum likelihood, right? And if you just cannot compute it, then then it's not even clear how you would train these models. Yeah, and and optimizing the likelihood is also difficulty. It's also difficult because of its normalization Z. Now, what is some intuition of what you should do when you train an energy-based model? So essentially, what you want to achieve is the following thing. So imagine you have this energy f of theta, and let's for now assume that the data dimension x is just one-dimensional, just to illustrate things. Right? So x is our data input, and so f of x would be then some sort of function or some curve. Now, initially, when you initialize your model, typically it will assign the wrong likelihoods to training data, and maybe assign high likelihoods to other data that you don't want to train on. So it's basically randomly initialized. And then, what happens then if the training data are actually assigned low scores or low energies, and the wrong data are assigned higher ones, then what you want to do is you want to push down this function in the wrong regions, and you want to pull up this function in the location where the training data are based. Right? So that then after training, you kind of have almost reversed the setup where the non-data have low likelihoods and the actual data distribution has high likelihood under that model. And remember, this is not the full likelihood. This is still sort of the unnormalized part. We still have to exponentiate it and then normalize it. Right? But this is essentially what you expect from the energy, right? So the energy or the negative energy should be high around the data regions and should be low everywhere else. Yeah, so what do we actually try to achieve? We want to maximize this energy-based model, which is again the exponential of f evaluated on the training data divided by that normalization constant z of theta. Now the problem is that if we increase the numerator, we also so we want to kind of increase the numerator, and that actually also because of the normalization constraint then also induces to decrease the denominator, right? So if we just pull everything up, then we're essentially violating the normalization constraint, right? So when we pull something up in energy, we have to push other areas down, because otherwise our resulting probability density would no longer be normalized, right? And that actually then also translates to this partition function z, right? So it has to compensate for the fact that if we just raise the energy everywhere, that this thing still integrates to 1. Yeah, the intuition is that because the model is not normalized, if we increase the unnormalized probability by changing the parameters theta, then this actually doesn't really guarantee that the training data becomes really relatively more likely compared to all of the rest. Right? It might still happen that everything becomes more likely, but what we really want to achieve is that the training data should become relatively more likely to any other input that we could provide into that model. Yeah, so in other words, we also have to take into account that the wrong data point, the data points that we don't want to model, are actually also becoming less in likelihood, right, once we train these models. So we need to push these energies down for these wrong data points. Okay, so the simplest algorithm, or it's not even simple, but one algorithm that is actually able to train these energy-based models is called contrastive learning or contrastive divergence. And that turns out to be fairly important. And we want to spend the last couple of minutes of this lectures to understand this algorithm. So what does it actually do? But maybe before that, are there any questions so far? Is it clear what we're trying to do and what the difficulties are? Yes.
You wouldn't have to necessarily do this sort of thing, but you have to like recalculate the normalization constant. Like, does that make sense? Like,
yeah.
Basically, just like maintain the normalization constant.
Yeah. Exactly. So the question was, Yeah, so what's sort of the role of the normalization constant, right? So could we, if we were able to compute the normalization constant, could we just readjust it in every learning step and we would be fine, right? Yes, that is exactly right. So if we were able to compute the normalization constant, the short answer is you could just do gradient descent on that function, and the logarithm of this expression results in the logarithm of the first factor minus the logarithm of that normalization constant. And if you could just compute both terms, you could just do gradient descent and you would be fine, right? And the problem though is that you cannot simply do gradient descent on this z, because z is simply unknown, right? And so the problem, so what we'll do here is we'll talk about algorithms that completely eliminate the role of z. So kind of learning algorithms that sort of manage to find gradients of that function without knowing z. So that's what we want to achieve. Okay, great comment. Okay, right. So how do we optimize these models? So the idea is essentially to get rid of z of theta by using a so-called Monte Carlo estimate. And that could remind you potentially of the problem of Bayesian inference, right? Because in Bayesian inference, we're faced with a pretty similar situation. We wanted to compute a posterior distribution that involved an intractable integral over latent variables. And and instead of trying to solve that integral, we sort of gave up and we thought about alternatives, right? And I said that one way to do that is Markov chain Monte Carlo sampling methods, and the other way to handle those were variational methods. And in some sense, we're faced in a very similar situation here. We just want to reinvent algorithms that simply completely get rid of that normalization constant, right? And Monte Carlo, unsurprisingly, is again one trick that does that. But I'll let you know exactly how that works. Okay, so we'll use some sort of Monte Carlo sampling eventually. But the main idea is as follows. Based on this intuition that you want to pull up the correct data instances, you kind of want to increase f around these vicinities, and correspondingly you want to decrease the energy at the other locations. Here's actually what we'll do, and I'll motivate why we do that in a bit. So what we do in the end is we will create a sample from our model, p theta, assuming our model is already in a particularly, almost trained state, or some initialized state. So we'll generate a sample from our model, and then we do the following update only involving f, no longer involving z. We aim to increase f on the training data. So we do a positive gradient step in the direction of f theta of the training data, and we decrease the loss function by subtracting the gradient of f evaluated on a fictitious data point, x sample, right? So this will essentially increase f in the places where we hope to increase it, and it will push f down in these kind of fake, unreal data points, right? Everywhere else, essentially, right? Now, at this point, it's actually not clear that this algorithm actually really optimizes the maximum likelihood of that model at all, right? It sounds more like a pretty heuristic approach, and we don't even know why it works. And what I want to do in the next slide is actually to go through a little mathematical calculation and show you that this is exactly what you should do. It's really the gradient step, a stochastic gradient step that really that really aims for maximum likelihood training of that energy-based model. Yeah, I think there was a question here.
Even when the model has been trained for quite a while, we still treat the samples from it.
Yeah. So the comment was it's weird that even though the model might be already pretty good, that it sort of treats these samples as random noise. So what would you have expected there otherwise? Like some random samples?
Maybe some perturbations of the training data, which are definitely not good.
Yeah. So the question was, could we, why don't we use some sort of perturbations of the training data here that are definitely not good? And yes, there are probably alternative approaches to creating negative examples. They might, though, result in a biased version of the objective, but it might still be a good heuristic to train these models. So we'll discuss that later. There's another comment here.
So you started out earlier in the lecture saying that it's difficult to sample from energy-based models and so they're different.
Good comment. So the comment was, like I said earlier, that it's actually difficult to sample from energy-based models, and now I'm sort of pushing that difficulty under the carpet. Right here, I say that I actually need a sample from that model, and I need it for training the model. So the answer is, first of all, so what I talk about now is not yet about sampling. It's first of all, I'll just kind of justify this update. We'll then talk about sampling from the model because it's a necessary step in here. And the answer is it's still difficult, but it's not as difficult as optimizing the model. So it's still possible to sample from the model. It just takes long, but it's possible. Yeah. Okay.
Going back to the point of using something
Mm-hmm.
I mean, it wasn't around at the time but recently there's been a lot of work on contrastive learning and like, different ways of computing.
Yeah. Yeah, so the comment was, yeah, go ahead.
If I'm not wrong, I think any X there would still maintain the correctness of the gradient.
Yeah, let's postpone that. Let's postpone that discussion, and then because like this update really emerges very cleanly from a little mathematical calculation. Yeah? Right. Okay. Yeah. Okay. So our goal is again to make the training data, relatively speaking, more likely than any typical sample from the model, and this actually will provide a training signal that we can use to optimize the model. Yeah. And as you recall, comparisons are easy, right? But it's just difficult to compute absolute probabilities. Okay, so let's go through this little exercise. So why is this gradient update that I wrote down the correct gradient update? Remember, if we could, we would love to be able to maximize the log likelihood of that model, right? Because that's in machine learning, that's always the best thing to do, right? That's our default training paradigm, to just maximize the likelihood of our model on our observed data set. Now, what is the log likelihood? Well, it's just the logarithm of that energy-based model. And if you take the logarithm on one, first of all, the logarithm of a product becomes the sum of two terms. The log of the exponential of the energy is just the energy. And then the log of 1 divided by the normalization constant is just the negative log of that normalization constant. Right? So this is really the objective function that we want to now optimize over theta. Oh, that didn't work. I wanted to build it up. Anyways, now we have to go through it one by one. So what do we, maybe it's even better like this. So what do we do? Well, this is the first expression that I want to motivate. So let's go through it slowly one by one. The first thing that I do only affects the second term, like the gradient of a logarithm is the gradient of z divided by z. So the derivative of logarithm is 1 over x. And then I have the inner derivative of z being here. Now, let's be a little bit more precise over what this gradient of z really means. So for that, first of all, I write down z as the integral over the exponential of the energy f, right? And then I have, as you see, I have pulled that derivative into that integral, right? Which I can do because those variables x and theta are completely unrelated, right? So now what I end up with is still having that 1 over z in front, but now I have an integral over the gradient of the exponential integrated over the domain of x. Okay. So what do I do next? I compute the gradient of this term using the chain rule. First of all, the gradient of the exponential of something just gives me the exponential times the gradient of that, of the exponent, right? And that's just the gradient of the energy of f, right? And now what I do is I stare at this expression and I realize that this is really an expectation, right? This is an expectation over that unnormalized probability model, the energy-based model, right? This is this is exactly the probability, the exponential of the energy divided by z, and I integrate over the domain of that probability density. And what I integrate is the gradient of f, right? And so I can really write that as an expectation under that energy-based model of the gradient of f. So I write that as the expectation of x sample, and then and having that former expression here. Now you see the last equation is actually only an approximate sign. So I haven't done anything to the first term the entire time, right? I only manipulated this gradient of log z. And in the last step here, what I did is I picked a single sample from that distribution and plugged it in here in order to obtain a Monte Carlo estimate of that expectation, right? So now X is a random sample drawn from the energy-based models, and this is a single sample Monte Carlo estimator of that exact expectation that you see before. Okay? And that's exactly the expression that we had before, right? So it's really that gradient update that we found to be most intuitive. In order to optimize the model, I want to increase f over the training data, and I want to reduce f over wrong data. And as wrong data, I choose samples from the model. Right. So that answers the previous question. Couldn't we pick any other distribution here? No. If you really want to optimize for the log likelihood, this is sort of the natural thing that comes out. Right. You have to plug in samples from that model. Now, I'm not saying that this leads to the best results, right? But it corresponds exactly to maximum likelihood training of these models. Okay. Any questions to any of the mathematics here, or the steps all clear? Yeah.
Could you explain how you started treating it as an expectation between the third and fourth line?
Yeah. So for an expectation of some function f can be always written as an integral over the distribution p of x times f of x integrated over x. Right? That's the definition of the expectation of f under p. And now p in this example is just the energy-based model. In other words, this exponential here, and then the 1 over z. So one logical step that you can add is actually to kind of just pull that z back into that integral. Then you would realize that this is now really the distribution with respect to which you compute that expectation.
I guess I'm confused about how you got that extra gradient term, or not extra, but how you got that extra term.
This one?
Yeah.
Yeah, if you sort of trace it back, so that came from the chain rule. So that, that was sort of the inner derivative of taking the derivative with respect to that exponential.
Oh.
And I got that expression by just writing down the definition of z and pulling that gradient into the integral. Yeah. All right. Yeah, great comments. Okay. All right, so now as we're done with this little exercise, have we solved the problem? No, we haven't. We've just justified a gradient update that maximizes the likelihood. It's based on some stochastic contrastive gradient signal. It's contrastive. It's called contrastive, by the way, because you're contrasting the real data from some fake data, right? So that's called a contrastive approach, right? But the thing that I kind of skipped over so far is how do we actually generate the samples, right? How do we even obtain these samples from the energy-based model, right? Remember, it's still a high-dimensional complicated distribution. And this will be answered next. Oh, totally. Okay. Okay, I'll take that. I don't know what happened here. Okay. Yeah, so let's answer that last remaining open question of how do we generate samples from the model. Well, here's once more the definition of that model. And because it's a distribution over a high-dimensional space, there's no direct way to sample from it, like from a Gaussian distribution, right? Instead, you have to draw on the toolbox of statistics and look into sampling algorithms that are actually able to sample from really high-dimensional distributions. That's something that obviously statisticians have thought about a lot. And this led to this world of Markov chain Monte Carlo algorithms, right? That are exactly constructed to generate samples from these otherwise intractable distributions. Yeah. So what is some intuition of how you build a Markov chain Monte Carlo sampling algorithm for that energy-based models? Well, it's again using the fact that it's hard to compute absolute likelihoods of data points, but it's easy to compute relative likelihoods, right? Because for relative likelihoods, P of x divided by P of x prime, these normalization factors canceled out. Now, this will be an ingredient in the following sampling algorithm that I derive. Now, how does this MCMC or Markov chain Monte Carlo approach work? Well, we initialize a sample x0 in data space randomly, for example, or in the origin or arbitrarily, whatever you like. And we also have an associated time index that characterizes for how many iterations the following procedure will run. And now what we do is the following. We first randomly perturb our initial state, right? Let's call it xt. That includes x0 in particular, right? So we take xt and we add noise to it, right? According to a certain strength. And that generates another fictitious data point. Let's call that new fictitious data point the noisy version of the previous one, x prime. Now, there are two things that could happen. Either we like it or we don't like it, right? Either it looks realistic, it got better, or it got worse, right? When it comes to making data that looks similar to the training data. What do I mean by that? Well, what I do essentially is I evaluate this energy function f in this newly created data point x prime, and I compare it to what I had before, x at time t. Now, when f of x prime is larger, if the energy is larger than before, it means actually that the model thinks that it's even more likely than before, right? So that's good because ultimately we want to create data that is hard to distinguish from real data. In this case, I accept this new data point and I call it xt plus 1. Right? So that's now my new iteration, the data point that I just generated in iteration t plus 1. Now, what happens if I don't like it? I might still accept that new data point, but with a lower probability, right? So what I'll do is I'll accept that update. So I said xt plus 1 equals x prime, but only with a certain probability, namely a probability that's proportional to the exponential of f of x prime minus f of xt. Now, the reason why I need that is that if I would not sometimes accept randomly created data points that are becoming less likely than before, I would quickly get stuck in a local optimum, right? And I want to escape from these local optima because oftentimes my energy landscape is really complicated and has many local dips that I don't want to get trapped into, right? And therefore, I want to have that small probability that I even accept data if in one iteration they're looking worse than before. Right? So that's why the second step is also needed. Yeah, and after that distinction, I just go back to step 2, and I try out another noise perturbation. I either deterministically accept it or I only accept it with a low probability, and that's how I kind of iterate. And ultimately, after many steps, I have done that sufficiently long time that my data point hopefully looks realistic, and I've just created a sample from my model. So there are two questions here. I don't know who wants to go first, maybe.
What do you do if you don't accept it? End the process, or do you just go back to XT?
Yeah, if you don't accept it, so if none of the two criteria are fulfilled, you just try out another noise, right? So yeah. Mm-hmm. Yeah, what's that?
I want to ask, cannot and this not be treated as a general framework for generating samples in discriminated settings as well?
Could it be set up for generating samples in a discriminative setup? What do you mean by like a discriminate, like samples in a
basic classifier,
mm-hmm.
like an image classifier.
Yes.
And you want to generate some feasible images. Could you not start with some random image and then keep on checking whether the connections or one particular table is going higher or lower?
Oh yeah.
Based on this
Right. Yeah, that's a good comment. So yeah, sometimes we're, you know, in certain fields of machine learning, we're interested in, you know, generating images that would kind of maximize the likelihood of some classifier, right? I mean, how does an image have to look like in order to be recognized as a stop sign, right? And of course, those could be sometimes used even to fool classifiers. And you know, can think of many examples of that. And yes, the answer is you could potentially run these kinds of algorithms to generate samples that obey certain criteria. In fact, there's some really interesting work recently that that is based on this idea of products of experts, where you have an unconditional generative model that produces sentences. And now you also have a classifier that tries to classify the sentiment of a sentence. And now you build a mixture of expert model, exactly in the way we describe it. And now it's no longer tractable, and you have to run these kinds of algorithms. But in the end, what you can do is exactly what you described. You can generate text that maximizes the sentiment, you know, that looks positive, that has like positive sentiment, for example. Yeah, it's a good observation. Yeah.
During training, you never explicitly compute Z, right?
That's right. Yeah, you never compute Z. Yeah.
You're doing inference, but if you need it, or
you actually really never need it unless you really explicitly want to compute the probability of a data point. Then you're sort of in trouble, right? However, it turns out that if anything else is perfectly doable, right? We just learned that we can train these models without knowing Z using these complicated schemes that I just described. And we also learned that we can generate data from these models, right? Both works without knowing the normalization constant. Yeah. You can also make comparisons, which one is larger or smaller. And that sometimes helps with, for example, anomaly detection, right? You could contrast a data point with other data points that you consider normal and see, you know, is it more likely or less likely than my reference set? Yeah.
I was hoping like this will come later, but this is like said that it won't be completely redirected. And I was wondering, for instance, for the icing model, how do you get the correct image? If you don't do the inference for that.
Yeah, so the question was for the Ising model, how do you get the correct image if you cannot compute Z? If you don't marginalize, yeah, it's tricky, but it's going also a little bit too far maybe. But to kind of quickly answer your question, you would actually run a similar MCMC algorithm. The only thing is that you would do simulated annealing, which means that you're, you know, the step in which you even accept data points that look less likely than before, that gets less and less frequent. And so basically on average, you're only accepting, over time, you're accepting only data if they look better. And it turns out that this sampling scheme will then get you to the minimum of that energy landscape. And so that would be then the most likely image reconstruction. Yeah, all right. There was one more question here. Yeah, once the training is complete, do we use the same algorithm for generating samples? Yes, pretty much. I mean, without the gradient steps, right? I mean, you would use this inner routine that you use in order to generate contrastive examples for generation, right? So it would be as expensive as a single gradient update of that model. Yeah, the question was after how many iterations do we stop that scheme? That is a complicated topic. You know, that goes into like convergence criterion of MCMC chains, and there's a lot of literature in the statistics. There are certain diagnostics that you can do. For example, you can run multiple chains of Markov chain Monte Carlo, and then look at their inner variance and their intravariances and compare them. And it's a deep topic. I mean, typically you would just decide on an arbitrary fixed number of steps for your gradient updates and see if it works, right? All right, one more question here.
So just to clarify, are we preserving the chain that we get between these gradient steps? Or are we starting from scratch every time?
You would. It's a good question. You might preserve the last sample because it might be a better initialization for the next step. Right. Yeah, you could put, in theory, you would kind of rerun this chain in every step, but you're right. I mean, so here I'm basically not kind of precise about what X0 is. And it might be a better initialization if for x0 you pick the previously generated x0 from your gradient descent schema. Yeah. Yeah. Okay. Could it cause the same issues of starting from a local minima? Yeah. Yeah, maybe. Yeah, you might. It might bias your result in some sense, because if there are many local minima, you pick the same one for initialization. Yeah, it's a little hard to predict. At some point it gets very empirical and you have to try things out. But yeah, there are issues that it might things better, it might make things worse. It's hard to tell. Yeah. All right, we're almost done. Yeah, pretty much at the end. Well, maybe was there one more question here? Okay.
Yeah, sorry. In the previous slide, is that probability is set in the step like 2-2? That probability that's sort of is that just heuristic, or is that like justified?
Yeah, so the question is if that here is a heuristic, or if that is that step really needed. It turns out it's really necessary to assure that you sample from the correct distribution. Yeah, I mean, that goes, if you're interested in that, you can look into the Markov chain Monte Carlo literature. There's this concept of detailed balance that needs to be preserved. And yeah, all of these updates are carefully derived, and you can actually show that this really converges to the right distribution. Yeah. All right, thanks for these great comments. And let me quickly wrap up. So what have we talked about today, and what have we learned? Well, these energy-based models are clearly a new class of interesting models for high-dimensional probability distributions. And I didn't really have the chance of talking a lot about sort of modern extensions. But I could, if you're interested, shoot me like a message and I can share some papers. It's a very flexible class of models. Much fewer constraints than, for example, in autoregressive models or even latent variable models. It's currently less popular because of computational issues, but I think this has even kind of changed a bit. So I would say they might actually come back. And yeah, so there are also kind of all sorts of hybrid models possible, right? I mean, there can be energy-based GANs and contrastive learning and in other models that we've talked about so far. So it's still like a very active area of research. There's actually a tutorial if you're interested in that. It's a little older, but Jan de Koon published a tutorial on energy-based learning, and I think this link should work, so to kind of get you there if you're interested in that. With that, I'd like to close. Thank you very much. I'm still here for your questions, and yeah, have a good weekend.